Hi, welcome everybody. So I would like first to thank the organizers, in particular Hoyoli, for inviting me to participate in this nice event. So I will be giving a talk about uniqueness of spherical metrics with some conical points. And so this is the first lecture in which I will review some background and some known results. In particular, the existence of such metrics. In the second talk, I will discuss about uniqueness of such metrics. So let's see what's the problem. So spherical metrics are just metric on the sphere, so we are not two-dimension, which have positive constant Gaussian curvature everywhere. So in some sense I will look for the prescribed Gaussian curvature problem, which is as follows. So if you start with a metric with a Gaussian curvature k0, and if you conformally change the metric with this conformal factor, which I express as exponential of 2u, then the new curvature will be given according to this rule. So you have a Laplacian, and then there is the new curvature k times the conformal factor exp, and then there is minus k0, which is the starting Gaussian curvature. And this is an equation on S2. So if you can find a solution of this equation, you can actually conformally deform your metric so that the new metric will have the prescribed curvature k. So what are the conical singularities? So these are somehow locally you will see a cone. So locally the metric will have this singular point, which is expressed as z with some power to alpha. Okay. So if you want to prescribe this conical point, you will have to look for solutions of this equation, where you have to put the singularity in front of the nonlinearity. And then there are some extra terms coming out here, which doesn't play much role. Alright, so in general, if you want to prescribe n conical points, so you will have to put n singularities. And so I will, from now on, write this as k alpha, okay, where I collect all the singularities in this function here. So k alpha will locally around the singular point be as a power of 2 alpha. Okay, so we will actually rewrite this problem in this more convenient form. So this is the mean field formulation of the problem. So I will write this as rho. I will introduce a new parameter rho here in front. And so I write rho times the nonlinearity, and then I divide by the total integral. Okay, so I do this, and rho will be just, of course, the total integral of the nonlinearity. So what is actually rho here? So the total integral of this nonlinear term, if you look at the equation, so if I integrate both sides, so for example up here, so the total integral of the Laplacian on the sphere, of course, is 0, and then I get that the total integral of the nonlinearity is just the integral of k0 plus this extra term. Okay, so I get this equality, and now by Gas-Bonnet, the total integral of the Gaussian curvature is on the sphere, in particular just 4 pi. So the parameter rho is rho is 4 pi, sorry, plus 2 pi, the sum of the singular powers alpha. So I will call this quantity the geometric parameter. So with this choice of the parameter, I return back to the original equation, the geometric problem. Okay. So what the idea is to study this equation, forgetting about the geometric problem, so forgetting about the motivation. So I will study existence and uniqueness of solutions for this equation depending on this parameter rho, which I will allow to vary. And if I want to get back to the original problem, I have just to choose rho to be this quantity, this geometric quantity. Okay. Okay, so from now on, I will consider this mean field formulation and will allow rho to vary. So how you show, for example, existence of solutions for this problem? So you can look variationally at this problem, since you can easily see that this equation is just the Lagrange equation of this functional. So solutions correspond to critical points of this function. So you have two parts, the Dirichlet energy giving the Laplacian, and then you have rho, which multiplies log of the total integral of the nonlinearity. Okay, so the derivative of log will give you this mean field term here. All the rest, okay, so k naught and this sum of alphas, I can just neglect it, will not play any role, provided that I restrict biatation to functions with vanishing mean value. Okay, so this is always possible because you see the equation is invariant if you add a constant to the function u. So I can just adjust the constant so that the functions have zero average. So this is the functional. So let's look at the critical points of this functional. So from when I will talk about existence, so rational structure of this functional, I will restrict for simplicity to the regular case, so no conical points, no singular points. So the k alpha will be just a smooth positive function k. So the basic ingredient in the study of this class of problems is the classical Moser-Turing inequality, which gives a relation of the two parts. So it tells you that the nonlinearity is controlled in terms of the Dirichlet energy. And there is a sharp constant of 4 pi here. So this immediately tells you that if the parameter rho is small enough, then you can have this control from below. So you just plug in the Moser-Turing inequality into the functional, and you see that it is bounded from below by this Dirichlet energy and this quantity. So you see if rho is smaller than 4 pi, this will be a positive constant, and so you have a bound from below. So in particular, for rho smaller than 4 pi, the function is bounded from below and coercive. So you can just minimize it and find a global minimum, and this will be a solution of the problem. So this is the simplest case, the coercive case. So what happens if you exceed this value? So if you are bigger or equal than 4 pi, the function is not coercive anymore. Actually, even not bounded for rho strictly bigger than 4 pi. So there is no hope to minimize it anymore. So one of the problems in looking for solution in this super critical case, so non-coercive case, is the bubbling problem. Indeed, it is well known that if rho is bigger or equal than 4 pi, so the solutions of the problem may blow up. On the other hand, we have a quite good understanding of the bubbling phenomenon, and what happens is that if you have a sequence of blowing up solutions, they will start to concentrate around these blow up points, and each blow up point will carry a quantized mass, say, so the mass of the sphere. So eventually you can show that this nonlinearity, okay, will converge to sum of Dirac deltas with mass 4 pi. So this gives you, in particular, a quantization of the, say, critical bubbling parameters rho. Indeed, if you integrate both sides here, you just see that the sequence of parameters rho n, which correspond to the bubbling sequence, will converge to a parameter rho which is a multiple of 4 pi. So if we are stay away from the multiples of 4 pi, then we know the solutions are uniformly bounded. So this will be crucial to find solutions of that equation. Okay, so the picture is roughly like this. So you start from the trivial solution in 0, and then when you, so this is the minimizer, okay, this red branch of solutions. So this will eventually blow up when the parameter rho will approach 4 pi, and then you will have other solutions blowing up around multiples of 4 pi, and then they are maybe solutions which stay uniformly bounded when we are far away from these critical values. So how about proving this the existence of this branch of solutions in uniformly bounded? So the idea is to apply some min-max arguments. So we consider rho bigger than 4 pi and not a multiple of 4 pi. So we have uniform bounds which will be used somehow as a compactness property for the min-max method. So we do not have here standard Palais-Mail conditions, so we need to use some other compactness property, and this is the uniform bound is the one which does the job. So the idea of min-max methods is quite simple. So this is a very easy picture. So we have this function like this, and you will look for topological properties of sublevels of this functional, so which are described here. So one sublevel is, for example, connected. The other one is not connected. So this change of topology will suggest you that there exists a critical point in between. Okay, so this is the idea. And this is what you prove for this class of problems. You study topology of, so homology of sublevels of the functional. So what you can easily prove is that this high sublevel is always contractible. Okay, so there is no topology, no non-trivial topology up here. So all the work you have to do is to show some non-trivial topology in the low sublevels. So the very rough idea is the following. So suppose we are in the first interval, so 4 pi, 8 pi, and we want to prove existence in this interval. So what you can actually prove is that if a function is in the low sublevels, okay, so lives here, you can show that then it needs to be concentrated around a point on the sphere. So this is done by using improved version of Moser-Turing inequality. So somehow, if your function is spread in two parts, then you can improve the inequality, the Moser-Trug inequality, and this will give a bound on the function. So if such bound does not exist, then this means that the function cannot be spread in two parts, so it needs to be concentrated around one point. Okay, so this gives you a criterion to describe the low sublevels. If you live in the low sublevel, then the function is concentrated around a point, and so then the idea is to map that point, identify this point. So each function in the low sublevels is you can map that function with a point on the sphere. Okay, so somehow you are able to describe the topology of the low sublevels by means of the topology of the sphere itself. Okay, and since the sphere has a non-trivial topology, this gives you non-trivial topology of the low sublevels, and this change of topology gives you existence of solutions. So this is just for the first interval, and you can generalize this to higher values of the parameter rho, but it's much more difficult. And this can be done not just for the sphere case, but for any closed surface. Okay, so this somehow gives the idea of existence of solutions for this class of problem. So actually you can show more. You can prove by Morse theory. You can count the change of topology of the sublevels, and the idea is that the more is the change of the topology, the higher number of solutions you have. So you can show that if rho approaches plus infinity, actually the number of solutions diverge. So you have many solutions for big rho. On the other hand, the question is, for rho small, do you have a uniqueness? So for example, the minimum that you have for rho less than 4 pi is the unique solution. So this is the question that we will try to understand. So the answer is yes, and there are several results in this direction with totally different methods. So I will address this question now in more detail. Okay, so we will prove uniqueness and discuss uniqueness in the second part of the talk. So this is the result that I will discuss. So thanks for watching this first lecture, and see you later.